Alright, today's topic is over similarity and transformations. We've already talked about similar polygons as it relates to their scale factors and the similarity ratio. This time we'll be talking more in terms of dilation. We know that dilation is the only of the four transformations that results in similar but not congruent figures. So this is where we'll be focusing today, is on our dilations. Alright, so first off, with the dilation, we know that we have a scale factor of some number k. If k is larger than 1, it is an enlargement, meaning that I am making my figure bigger. If k is less than 1, then it is known as a reduction, and that would be making it smaller. So notice here, though, around the k, we have two lines. These are what we call absolute value signs. So for example, if I have k equals 4, 4 is larger than 1, so this is an enlargement. If I have k equals 1/3, k is less than 1, so that is a reduction. Now, if I have k equals -2, okay, this is where the absolute value comes into play. The absolute value of -2 is 2. Remember, absolute value will always be positive. If it's a negative, it changes to a positive. If it's positive, it stays to the positive. So since the absolute value in this case would be 2, then this is what we're looking for, and it would be an enlargement. Okay? So you got to be aware of that. Alright, so this is what I have for you. This is an example of an enlargement. The red figure is my original figure. The blue figure is the enlarged figure. Alright, the red figure over here in the reduction area is my original figure. Notice it's the same figure, but this time I've reduced it. I have a reduction occurring here, so the blue figure is smaller. When I have a negative k value, what ends up happening is not only am I either an enlargement or a reduction, but I also am going to end up rotating around. Okay? Now, dilation will always preserve angle measures. Excuse me. Basically, when I take a figure, so let me grab a figure real quick. Alright, so let's use this figure, the star. Okay, if I were to copy this figure and dilate it, okay, the angle measure that you see is still going to be the same. So let's take a look at this angle measure here. Okay, so what I'm going to do is I'm going to group these items together. This angle measure should be the same for this angle measure here. Alright, so what I'm going to do is I'm going to line it back up, and you'll notice that the two angles measures actually overlap. That is because dilation preserves the angle measure. Okay? Alright, so let's go ahead and try some practice of doing some dilations. First off, I know my scale factor is 2, so this would be what we would call an enlargement. So first off, I would multiply every x and every y by 2. Alright, now I'm going to graph the first one. Oops, there we go. So 2, 1 to 2, 3 to 5, 1. Alright, so that is my original figure. Alright, now I'm going to get a different color line and do my enlargement. So 4, 2, 4, 6, and 10, 2. Alright, so there you have it. That is your enlargement with a scale factor of 2. Alright, so let's try this one. This time the scale factor is 2/3. Since it's less than 1, we know this to be a reduction. Alright, so let's go ahead and multiply all of our x's and all of our y's by the scale factor 2/3. And this is my p prime, q prime, and r prime. Alright, so let's go ahead and plot these points. Okay, so negative 6, 3, negative 3, 9, and 3, 6. So all the way over here. Alright, so there's my picture. Alright, that is the original figure. Let's get a different colored line and draw my reduction. So negative 4, 2, negative 2, 6, and 2, 4. Alright, so what we have here are two similar figures, where the red is a reduction on the black. So a similarity transformation is any sort of transformation that occurs, but it has to include a dilation. So I can rotate and then dilate, I can reflect then dilate. As long as I have dilation somewhere in the transformation, it is considered a similarity transformation. It is not a congruent. Remember that dilations do not make congruent figures. So two figures are similar if and only if there is a similarity that matches one to the other. So we are going to use this information to determine if two figures are similar. So first and foremost, let's go ahead and map our two figures. So I'm going to map the first one. So A is negative 3, negative 3, negative 3, 6, 6, 6, oops, that line didn't want to work with me very much. There we go. Let's see, what else do we have? Get back my line tool. 6, negative 3, and then connect it. So there we go, there's my quadrilateral. I'm going to get a line and get a different color, and this time we're going to be using red for this one. So negative 2, 4, 4, oh, negative 2, 4, excuse me, 4, 4, and 4, negative 2. Alright, so there are my figures. Now, I can tell this is probably going to be a dilation, but I need to figure out the ratio. In order to find the scale factor, I need to go from one point to the other. Alright, so let's use C and K. What do I multiply 6 by in order to get 4? So I would divide both sides by 6, and in my calculator this simplifies to 2/3. So now our job is to go back and make sure that when we multiply every number up here by 2/3 that we get the numbers down here. Okay, so let's go ahead and give that a shot. Let's see. Negative 3 times 2/3 gives me negative 2. So that works. A is the right scale factor for H. It also works for this point here, negative 3 to negative 2. And then 6 times 2/3 is 4, so that gives me B to J. We already know that C and K map on, so we really just need to look for L. So 6 to 4, yes, that works. We've already done the math there. And negative 3 to negative 2, we've done the math there. So because I can use the scale factor for all 4 points, I would say that yes, this is a dilation of a scale factor, of 2/3. Alright, so let's try the next problem. Go ahead and graph these, pause the video, and then restart once you have them graphed. Alright, so if we take a look at the first rectangle, I notice that this has a side length of 2, and this side length is 1, 2, 3, 4. Alright, so then I want to look at this rectangle, and I have 1, 2, 3, 4. Oh, so what I'm seeing here is that the height of both of these rectangles, it looks like I've multiplied by 2. So if I multiply 4 by 2, I should get 8. So the question is this distance 8? So 1, 2, 3, 4, 5, 6, 7. Unfortunately, that means that these are not similar. there is no dilation that I can use to map the black rectangle on top of the red rectangle. Okay? Alright, so I wanted to take a minute here, and I want you to go ahead and graph these two. Pause, and then unpause when you have them graphed. Alright, so we have two figures here. We can check their side lengths. This is a 1 by 2. And this is a 1, 2, 3 by 1, 2, 3, 4, 5, 6. Okay? So the actual transformation that is happening here is I'm going to take this triangle here and I'm going to shift it left 3 and up 1, or excuse me, left 5. So I go 1, 2, 3, 4, 5, and then I'm going to go up 1. And then with a center around the origin, I can dilate this with a scale factor of 3. I know that because this side is 1, and to get 3, I multiply it by 3. This side is 2, multiply that by 3 to get 6. You can check your work here. Basically, you would take the points of this one. So negative 1, 2, negative 3, 2, and negative 1, 3. Multiply all those by 3, and you will get the points that you see here. Alright, so dilations can also occur not just in any number of polygons, but actually it can occur in a circle as well. So, given circle A with a center of 0, 0 and a radius of 1, is similar to circle B in center 5, 0 with the radius of 2. Now remember, we can prove things are similar by being able to do a similarity transformation. So what I would do here first is I would take this circle, let's go ahead and copy it, and I would actually move it to the right 5 because I want to center it at 5, 0. So 1, 2, 3, 4, 5. Okay? Then, taking this circle that I have dilated or translated to the right 5, I can dilate it with a scale factor of 2. Okay, so this isn't going to work on this map. But if I were to double this in size, okay, all the way around, the radius should go from 1 to 2 all the way around. Okay, so yes, these circles are similar. All I have to do is translate to the right 5 and dilate by a scale factor of 2, because the scale factor will change the radius from 1 to 2 all the way around. So it won't let me show you by stretching it out. It's weird like that, but alright, so let's do another circle. This time the center is going to be at negative 2, 0 and with a radius of 2. The circle at 4, 1 and a radius of 1, 2, 3. These are similar, okay? So in order to line up the centers from negative 2, 0 to 4, 1, I'd have to go to the right 6 and up 1, and then I would need to multiply by a scale factor of 3/2 because the original radius was 2, and 2 times 3/2 will give me 3. So that is your scale factor. So, can you come up with a circle E that is not similar to circle F? Pause and think a minute. This is actually a trick question. There isn't one. The reason why is that all circles are similar. Basically, all circles, if I have a radius of 1 or 2 or 3 or 4, it's the same shape, just a different size, isn't it? So, all circles are similar. So I got a really funny joke here for you. It says, circle 1 says, I'm so enlarged lately that I don't even want to tell you my scale factor. Circle 2 says, don't worry about it. All circles are similar. Alright, so to leave you on that funny little joke, who knows? Maybe I'll ask you the punchline for tomorrow, that all circles are similar. Alright, I will see you guys later.